In the last video we looked at circuits with resistors and inductors. Now we're going to look at inductors and capacitors, and then all three: resistors, inductors, and capacitors. We're going to start out by looking at our good old circuit construction kit. Here I have a ready-made circuit with an inductor and a capacitor in it. So first off, I'm going to keep the inductor out of the circuit, and I'm just going to close this here and charge my capacitor. Now that that's all done, I'm going to disconnect the battery so it's out of the picture and connect the inductor to the charged capacitor. And as you would expect, the capacitor is going to discharge, but now the inductor stores some energy and it will give it back to the capacitor, and essentially the energy will slosh back and forth between the inductor and the capacitor, being stored in the electric field of the capacitor and the magnetic field of the inductor. And if there's no resistance whatsoever, you will just get this nice sinusoidal current going back and forth between the two. So here's the circuit we just looked at with just an inductor and a capacitor, and we can analyze the dynamics of this system by starting out with a Kirchhoff voltage loop. If I loop across my inductor, the voltage across that is negative L di dt, and then the voltage across the capacitor is Q over C, and that has to sum to 0. Those are the only two components we have. I also know that my current is going to be negative dq dt, and so if I plug that in here, I get second derivative of charge with respect to time, and I'm going to divide both things by L so that both of my constants are here under my Q, and I get an equation that looks like this. Now this is very reminiscent of an equation we got when we were doing mechanical oscillations. With mechanical oscillations, we started out setting F equals ma, or applying that to a spring force, and we ended up with an equation that looked like this: the second derivative of position with respect to time plus x over m times k. So pretty similar situation, and this was equal to 0. And what we did was we guessed a solution, a sinusoidal solution, then we plugged it back in, and that's what we're going to do here as well. I'm going to skip a few of the steps, but our solution will probably look something like this, where we have some initial charge, and then that represents the initial charge of the capacitor, and then that is going to oscillate. We'll use a cosine function because we want the initial to be at the maximum, plus some phase angle, where omega is the frequency at which the energy essentially is oscillating back and forth between those two things. So if we take the second derivative of this with respect to time, plug these things back into the equation, we end up with something that looks like this: negative omega squared plus 1 over LC, all of that times our cosine function, and this thing has to equal 0 because that's what we plugged back into this equation and got. Now the cosine equals 0 occasionally, but certainly not at all times, so the only way that this equation is always true is if this part equals 0. That's a really ugly curly bracket thing, but if that part is equal to 0, we get that omega is equal to the square root of 1 over LC. And we followed a really similar process for mechanical oscillations, where we found that the frequency of this oscillating system was 1 over, or square root of k over m. Okay, and this is also equal to 2 pi times the frequency, because omega is always equal to 2 pi times the frequency. So here's our equation that we just looked at. We guessed the solution to that differential equation, plugged it back in, and found that it was indeed a solution as long as that limit on our frequency was satisfied, 1 over LC. Okay, we can take the derivative of this guy to get an equation for our current as a function of time because of this relationship here. And we can replace omega Q naught with I naught because that's going to represent our maximum current. When the sine portion of our equation goes to 1, that's our maximum current. So both the charge on the capacitor and the current going through the inductor will be sinusoidal. They will be off by what we call a phase angle, so they're out of sync, but they still have the exact same frequency. Now if we look at the energy stored, the energy will be all in the electric field, and then that will decay down to 0, and when that does so, then all of the energy ends up stored in the magnetic field. Right here you have it split half and half, and at any moment in time, say we take right here, you would add this and you would add that, and those would sum to this total amount of energy. So we have a constant amount of energy. As long as there's 0 resistance, this thing will perpetually oscillate. If we want to get some equations for that energy, well, we can say the electric energy is 1/2 q squared over c. And if we plug in the equation we just found for q, that works out to be q naught, or the maximum charge, over 2c times cosine squared of omega t plus phi. And then if we look at the energy in the magnetic field, that's going to be 1/2 Li squared. And if we plug in the equation we had for I, this one's a little bit messier, but we end up with L omega squared Q naught squared all over 2 times sine squared omega t plus phi. And then if we use our expression for our frequency, our angular frequency of 1 over LC, and we plug that in here, so we're going to square that, and then essentially this guy goes away. We'll end up with an LC down here. The L's go away, and so we have Q naught squared over 2C. So we end up with the same coefficients out in for the same constants out in front here. So the total energy at any moment in time is going to equal the sum of these two energies. And so we can go ahead and write Q naught over 2C cosine squared omega t plus phi plus, I'm going to have to squeeze this guy in here, Q naught, oh, I forgot the squared here, over 2C sine squared, and you probably see where this is going, plus phi. So you would use either of these equations here if you wanted to know how much energy was stored in either the inductor or the capacitor at a given moment in time. But if we're just interested in the total energy, then it's convenient that we can factor out the Q naught squared over 2C, and we're left with a cos squared. I'm not going to bother writing all of the other junk. So we end up with this, and everybody knows that that goes to 1. So if we know the initial charge or the maximum charge on the capacitor, the two are synonymous because you're not ever going to end up with more charge on the capacitor. I guess if you start with some energy in the inductor as well, but that would be kind of a strange situation. Anyway, if we know the maximum charge on the capacitor, you can just square that, divide by 2C, and that will give you the total energy of the entire system. Alright, now if we have a very similar circuit but we add a resistor, you can probably guess what's going to happen. It's still going to oscillate back and forth, but we're now going to start losing some energy because this essentially will be creating some heat. We also have to add an additional term, this one right here, where this is I times R, and we wrote I as dq dt. So this is going to change our equations a bit. I'm not going to go through all of the math because you're probably getting tired of it, some of you. Anyway, you end up with this as a solution to your equation, which looks just like our other expression, except for you've got this additional term, essentially of a decaying exponential. It also affects your frequency a little bit. You add this term here, so you're subtracting off something, so you're actually going to end up with a slightly smaller frequency. And then we define different types of oscillations. These are called damped systems when you have resistance, and this kind of came from the mechanical situation. We actually didn't look at damped mechanical oscillations, but they work out very similarly. So the idea is if it's underdamped, so that means it's damped a little bit but not so much that it actually stops the oscillations, then it's going to follow this curve here. It's actually still going to oscillate, but we would say that the oscillations are being attenuated. They're shrinking as we go. And then we have critically damped, which is defined as essentially doing one single oscillation and going down to 0 as time approaches infinity. And then we have overdamped, where it never really even gets there, never gets down to 0. And we can get those expressions by, well, we can, not those expressions, we can decide which type of damping we have by looking at r squared versus 4L over C. Or if you prefer, you can divide the RC across, and then you're going to compare. In this case, it would be greater than 1 anyway, so you got 4L over r squared C. Sometimes it's kind of easier to just calculate this rather than and compare it to 1 rather than comparing the two sides. But either way, you can always plug this in and figure out what type of damping you're going to have. So you might have a question that says, do oscillations occur? And what you're going to want to look at is this relationship between r squared and 4L over C. And if this is satisfied, then you say, yes, the oscillations do occur, and they're going to occur with this frequency here. Okay, see you in the calculations.